Hi, how are you?
Good to see you. I'll give another half minute to get more people added in first. Okay, maybe that's it. So hi, welcome back. I'm glad to see everyone who's here. Oh, here comes Joe B. And things are getting serious now. We're in the middle of we're just at the very beginning of talking about surface integrals, and boy, that's where all the stuff that you've learned all semester is all coming together in this just beautiful sort of culminating orchestra. And so we're about to get into it, but I just wanted to remind you a couple of things before we do. So I sent out that poll over the weekend, not poll, but sort of form to fill out about whether you'd like to take the exam 4 with a partner or not, and what day you'd like to take it on. One of the days is for one of the classes, one of the days for the other class. I don't know which one. It doesn't matter to me which one you take it in. You may want to take it early and be done. You may want to take it later and have time to practice. It doesn't matter to me. So, but what does matter to me is you need to say it by Wednesday at noon. Because I need to see whether I can even find partners that work and then set people up for it and so on. So I really can't wait past that. So if you don't manage to respond by Wednesday at noon, then we're just going to go the default. Then you will for sure just be solo on the day that you're assigned, and so there won't be any surprise changes for you. You just won't have an opportunity to do other things. Also, somebody filled out the form on Sunday, but they didn't put their name. And so without their name, I can't I can't take your input. So if you think you did that, maybe submit it again. And if you put your name on it, and if you happen to not be that one, but you submit twice, then I'll be like, well, I'm not gonna count this person twice. I'll just take the first one. Okay, and then the last thing is, if I'm able to do partners, then I'd like to connect everyone with their partners Thursday at noon, so you'll have at least a week, more like a week and a half to get to know each other, maybe work together, that sort of thing. And the way I'm going to do that is just by, I used to do that in person by I'd have the students meet up in class, but since we sure can't do that, I'm just going to send you each other's emails. That, without your permission, that would be a violation of privacy. And so I don't want to violate your privacy. And so I'm just going to announce now that that's my plan, but you can opt out of that, and then you'd have to have another way to connect your partner, I guess. But you'd have to let me know before Thursday at noon. You can opt out, and otherwise your partner's going to know your email address, basically. All right, so that's all the admin. Does anyone have any questions before we get going on new exciting things? No. Oh, look at everybody. It's so nice to see you all. Okay, I like having some of these videos on. All right, let's talk about, last time we were doing section 13.6, we were talking about surface integrals. I don't remember what the title of this was. It might have been surface area, parametrizing surfaces and surface area, something like that. This is what we did, whether that was a title or not. Parametrizing surfaces and surface area. And we did one example, but I thought maybe it would be help to do one more example before I sort of threw you into the fray doing these all on your own. So let's just remember what the formula was. And the formula will kind of give us a list of steps that we have to follow. So recall from last time, if we have a parameterization, so let's suppose if R of U and B parameterizes some surface S. And I should be a little careful because remember, whenever we have a parameterization, I should also include the bounds. So let me just put that here. So if I have a parameterization of the surface, then the area of that surface. So the area is double integral of the magnitude of the cross product of the partial derivatives of that parameterization with respect to u and v. We did one example last time where the surface, oh sorry, and that's u goes from A to B, B goes from C to D. We did one example last time where the surface was a sphere and we calculated the surface area of the sphere. I think we didn't finish the calculation, but we did everything except what ended up being a pretty easy integral. So I know that's one that you can do. Let's just think about, so I talked to a student in office hours a few minutes ago, and I think maybe some of this notation wasn't totally clear. So let's just go through what this is, what this formula is telling us that we need to do in order to calculate the area. So first, notice these pieces. We have R sub u and R sub v. So, well, where did they come from? Well, I guess I needed the parameterization first. So this is kind of a hidden first step. So let me just say the steps. First thing, you're going to have to parameterize. And you're not going to be able to parameterize without a picture. So really, I'd say the first thing is draw a picture. If you don't already have the surface parameterized, you have to draw a picture of it. And to do use that to come up with a parameterization. With the bounds. This is something that we practiced a little bit, and you'll get better at the more problems that we do, and we'll do a lot of problems together. After we do that, how do we get these pieces? Well, I'm going to need to take the cross product of something. These are the partial derivatives. So I'm going to take the partials R sub u and R sub v of the parameterization formula. And then you can tell what do I have to do? I have to do the cross product and then take the magnitude. And then integrate. It's a lot of steps, but we know how to do all these steps. So, so we just take a deep breath and do it. Does anyone have a question before I start an example? Let me get the chat window up in case you want to say something there. Yeah, I think let's do an example, another example. I think that's going to stimulate maybe some more questions. So how about this one? Find the surface area for the cylinder of height 2, radius 2, with no lids. Okay, so what am I talking about? Let's put that cylinder, let's center it at the origin. So I'm drawing a picture. So a cylinder, this is, I haven't, this isn't a cylindrical parabola or anything like that. It's a standard cylinder. And so it's going to look like and the height is 2 units. So that means that this is going to be z equals 1, and this is going to be z equals -1 if I decided to center it at the origin. Or I could have set it on the floor, the XYZ plane, and moved it up, but this is fine. And then the radius is 2. Okay, so I've drawn a picture, and now I need to parameterize it. Somebody's excited about this parameterization. So, so how do you parameterize it? Well, the things that you need to know how to parameterize from before. Can anybody remember any of them? One of them was planes. What's another one? Anybody remember?
Sorry, what was the question?
The things that you need to know how to parameterize.
Oh, graphs and graphs of functions, spheres, and then things with round cross sections.
Things with round cross sections. Excellent. So let's see. This thing isn't a sphere. It's not a plane. It's not a graph of a function, but it is a thing with a round cross section. So so we can parameterize it like that. What are good coordinates that we need? So things with round cross sections, we might want to use cylindrical coordinates, makes sense. But one of those coordinates actually is a constant and not a variable in this case. Which one's the constant?
The radius.
Radius, yeah. So we're just going to use theta and z as our parameters. So r of theta and z. And we need to describe the x value, the y value, and the z value, all in terms of x, y, all in terms of theta and z. So let's see. The z value is just z, so that's pretty easy. And then the x and y value, well, that's the round cross sections part. Since we have roundness in the x, y direction, I can just use the ordinary 2 cosine theta, 2 sine theta. And then bound, let's see, theta goes from 0 to 2 pi. What about z?
-1 to 1.
-1 to 1. Okay, so there's parameterizing, that's the first step. And then now when we look at this whole formula, you don't need to memorize these steps. You just know in order to build this up, you're going to have the partials before you can take the cross product, before you can take the magnitude. So let's do the partials. So we're going to find r sub theta and r sub z. Those are our parameters now. So r sub theta, look at each of these pieces, each of these components of the parameterization with respect to theta. That's going to be -2 sine theta, 2 cosine theta. And z is a constant when we're taking the derivative with respect to theta, so I just get 0. R sub z is, well, theta is a constant with respect to z. So 2 cosine theta, that just goes to 0. 2 sine theta also goes to 0. And derivative of z is 1. Now we need the cross product. Get the normal vector. So r theta cross rz. So I've got -2 sine theta. Oops, I need more space. 2 cosine theta and 0. And then we take the cross product. So you're good enough at this by now. I'm just going to write it down, but you can do this. You know how to do this. So I've got 2 cosine theta minus 0. And then I've got 0 minus a minus. So that's going to be plus, let's see. Yeah, minus a minus and a minus. Oh my gosh. Wait, nope. It's minus a minus. So it's going to be plus 2 sine theta. And then the k is going to be 0 minus 0. Let's just take a reality check for 1 second. So think about this vector. Remember when we were developing it back on Thursday, this vector, the magnitude of the vector represented a little patch of the surface, represented the area of that little patch of surface. And the direction of the vector itself, what's the direction of the vector? Can you remember?
Wait, what was the question?
Yeah, so when I'm thinking about, I'm just trying to get some perspective on the meaning of this and whether our answer makes any sense. So r theta cross rz, when we did these cross products, what does the cross product of 2 vectors give us?
A vector that's perpendicular to both of them?
Yeah, vector that's perpendicular to both of them. So what we're going to get when we do this cross product is we're going to get a normal vector to the surface. And if I think about this, surface, any normal vector is going to go straight out in the z direction, horizontally. It's not going to change in the z direction. It might come at us if it's at some point in the front. That doesn't look exactly right, but it might come at us or further away from us, but it's not going to be up or down in the z direction, even though that picture looks like it. Okay, so that, I feel comfortable that I got a 0 value in the z direction. That makes sense to me in terms of the picture. I need the magnitude of that now. So let's see, magnitude of r theta cross rz is the square root of 4 cosine squared theta plus 4 sine squared theta plus 0. And I know sine squared theta plus cosine squared theta is 1. So if I factored out a 4, I'd get 4 times 1. So the square root of 4 is 2. The last thing is calculate the area. The area is the double integral of the magnitude of r theta cross rz d theta dz, where theta went from 0 to 2 pi and z went from -1 to 1. We set those bounds earlier when we parameterized the surface. But this is just the integral of 2. So let's see. Oops. Antiderivative of 2 with respect to theta is 2 theta. And then that's going to be -1 to 1, 4 pi minus 0. And then antiderivative of that with respect to z is 4 pi z. That's going to be 4 pi minus -4 pi. So 8 pi, that's the area. Does anyone want to ask a question about this? Is there something I could explain better?
If you were to switch the bounds on the integral, so like if you did it dz d theta, would that also mean you'd have to switch the order of the cross product?
Oh, that's a great question. That's not true. You wouldn't have to. And what would happen, so if you dz d theta, that has the same effect that it did back when we were doing double integrals. Sometimes something can integrate more easily one way or the other. Sometimes the bound setting up is better one way or the other. So those have the same independence, they always didn't. What would happen if we switched the order right here, if we made that rz cross r theta? Well, let's just think about how vectors work. So whenever I had 2 vectors and I took their cross product, the cross product pointed in the direction given by the right-hand rule, so the direction of my middle finger. So if this one was r theta and this one was rz, and I did r theta cross rz, then my cross product vector would point this direction. But if I did rz cross r theta, I would just have the cross product vector going the exact opposite direction. So the only thing that would be different is I would have it, so for rz cross r theta, oops, that's too dinky. I would have a vector pointing opposite r theta cross rz. But with the same magnitude. So in this case, since it has the same magnitude, it wouldn't matter which way you did the cross product. But something that you just said, Delaney, actually is going to foreshadow something interesting, and that's going to add an extra piece of thinking whenever we're talking about general surface areas with vector fields. So I'm glad you called attention to it. The order you don't have to choose a specific order, but once you've chosen an order, you have to check whether it matches or not. The same way that, remember when we did line integrals of vector fields, there was an orientation question? That we'll have that same kind of thing with surfaces, but we won't see that maybe until later today or tomorrow. For now, it doesn't matter which order you do it in. So, so either r theta cross rz or rz cross r theta are both fine. And independent of what order these are in. That's a good question. Anyone else want to ask something? All right, well, that's what I wanted to do with the warm-up surface integrals, but don't worry, we have a lot of surface integrals to do between now and then. So if you feel a little bit uncertain, you'll have so many more examples, it will start to feel a little bit better. So finding surface area, that was, that's sort of an interesting question, but that's not where the real richness is of this subject. That's just sort of an introductory type of calculation. Now we're going to get into the richness of it. So in section 13.7, just called surface integrals. And this is going to parallel the situation that we had for line integrals pretty carefully, actually. So remember, for line integrals, we had two types of line integrals. There was line integrals of real valued functions and line integrals of vector fields. Same thing's true for surface integrals. So we're going to have two types of surface integrals. Those are going to be surface integrals of real valued function and surface integrals of vector fields. And so we're going to talk about, sorry, hold on. I've got so many screens open, hold on a second. Okay, I forgot to put do not disturb on, but now no way will disturb. Okay, so let's talk about real valued functions first. Okay, well, these surfaces that we're dealing with, these surfaces are going to be sitting in 3 space somehow. The only surface that doesn't sit in 3 space is the one that's actually, in the XY plane. We can do those too, but in general, most of the surfaces will need to be in 3 dimensions to live. So our general situation is we're going to have a function which takes 3 inputs, multivariable function, but the output is a real number. That's what it means to be real valued. So let's say is real valued function. And I have some surface S. And let's say that surface is parametrized by R, B, and B. Okay, so what does this even mean? So I've got a function. Remember, if I have a real valued function that on all of R3, what that means is that every single point in R3, this function is giving me a value to. So maybe the function tells the temperature at this point, or the temperature at this point, or the temperature at this point. Or maybe we're measuring, maybe we've got some solid and it's giving us the density at each point. Or there's lots of sort of values that you could be thinking for all points in space. And then we have some surface, I don't know what it is, some surface like this. And what I really care about is the value of that function at each point on that surface. And integrating is, as we've always said, integrating is just sort of adding up. So in some sense, we're accumulating the value of the function all over that surface. And that's what the surface integral is. So in this case, the surface integral well, here's the notation. It's f ds. And notice that's a capital S. And we had that notation last time, but let me just remind you what that D capital S is. first of all, just like we did for line integrals, remember we put everything in terms of the parameter t. We put this function, we represented it in terms of the parameter t. The dr or the d little s, we represented in terms of parameter t. It was a one variable integral with t, the parameter being that one variable. Here, we're going to have a two variable integral with u and v being our two variables. So everything has to be translated into u and v. That means f is going to be evaluated at this parameterization. So it'll be in terms of u and v. And ds, remember, is the magnitude of ru cross rv, u dv. So in case you don't remember from before, let's go way up here to this definition. This thing right here, this was our ds, which was our surface area element, or surface area differential. Okay. I'm only going to say this and not write it down. I want to give you a feeling for this. Think about how integrals have worked since you very first learned about integrals. Maybe I'll write a tiny little bit down on the side. Okay, since you very first learned about integrals, you had this situation, and you had some interval, and you split it up into subintervals. What were you really doing here? You chose some heights. That's fine. Let's say I chose the right-hand endpoint. What you really did was, to find the areas of these three rectangles, you multiplied the width by the height. I should have said height times width. Do you mind if I just rewrite that? It means the same thing, but it'll look better. And where did the height come from? The height came from the value of the function. Somewhere. Where did the width came from? The width was the size interval that we're pretending that value of the function represents. So, here we are pretending that this value of the function right here represents the value of the functions all along this whole interval. So for all these x values, rather than just for this value right here. It has the disadvantage that, well, it's not the right f value. It has the advantage of, hey, we can calculate this area and we can do some estimates. Okay, so size interval that this f value represents. The width, the size of the interval. We're doing the same thing here. It's the same thing. This is the value of the function. And we're multiplying it by the size of the surface that value is meant to represent. And what do I mean by the size of the surface? The ds is a little patch of surface area. So this thing is size of surface. That function value represents. So I just want you to realize that we're just generalizing the same idea that we had back at the end of Calc 1, beginning of Calc 2, to a situation that admittedly is more complicated, but it's not a different idea. It's just an expansion of the same idea. Okay, so this is what a surface integral is. And you might as well mark this in bright green, or we don't need this part, because we'll be using that. Let's use it right now. How about this example? Okay, so I'll just put this away. Let's evaluate the surface integral of the function f of x, y, z is z over the surface, x equals y plus 2z squared, 0 less than equal to y less than equal to 1, 0 less than equal to z less than equal to 1. If I look at this formula right here, this formula tells me everything I have to do. There's a lot of things to do. It tells me everything I have to do. If I'm gonna, I have to plug in the parameterization of this function, so I better parameterize. And then I also have to take some partial derivatives, take a cross product, take a magnitude. Let's just do it all. So the first thing we should always do is parameterize.
What are you doing? I'm doing a seniors.
And somebody, if they have their, if there's noise on the background and your, yeah, there you go, thanks. Yeah. Okay, so let's parameterize. How are we going to parameterize this? What kind of thing is it? Do we have a thing with round cross sections? Do we have a plane? Do we have a sphere? Do we have a graph of a function? What is this?
A hyperboloid.
It would be, if there was an, I think I would need more squares for it to be a hyperboloid. The x isn't squared and the y isn't squared. What else could it be? Is it one of those things? Does it have round cross section? Is it a plane? How do you know it's not a plane?
Each of your values need to be squared, and your the sum of the three variables has to be equal to 0.
So if it's a plane, then none of them can be squared. And since one of them is squared, then you know it can't be a plane. But then, Joe, you're right. If it's going to be have a round cross section, you would need those to be squared. And they're not all squared, so it's not that. It's a graph of a function. So how is it a graph of a function? If you look here, x is represented in terms of y and z. So y and z can be the two parameters, and then x is just the output. So we're going to parameterize like graph of a function. And so let's use y and z as our parameters.
We know that it's a graph. We're parameterizing a graph of a function because it says f of x, y, z is equal to 0. Is that what you're saying?
No, actually, that's an independent thing. So this part right here, this is the integrand. But the surface was described to us like, and when I look at the formula for the surface, I already have x expressed as a function of y and z. So this is the part that I'm seeing as the graph of the function. I'm glad you asked for clarification. Okay, so then what is r of y and z? Well, y is just y. Z is just z. But x has been written in terms of y and z. X is y plus 2z squared. Graph of function. So, and then the bounds for y and z, those are given to us. Does that make sense? Okay. What's the next thing? What do we need to do now?
Take partials with respect to y and z.
Yeah, exactly right. So partials, so find our y and our z. Okay, so r sub y is 1, 1, 0. R sub z is 4z, 0, 1. And then, you know, go back to this formula. We're going to need the cross product of them and then the magnitude. So let's just keep going. Ry cross rz. Maybe I should say some words here. Right? So ry cross rz is ijk 1, 1, 0, 4z, 0, 1. And the I component, I get 1 minus 0. The j component, I get 0 minus 1, right? 1 minus 0. J component is 0 minus 1. And the k component is 0 minus 4z. And now I need the magnitude.
Isn't it negative 4z?
Yeah, thank you for correcting that. Yes. Okay, so then that's going to be 1 squared plus negative 1 squared plus negative 4z squared, all square rooted. So that's going to be 1 plus 1. That's going to be 2 plus 16z squared. Whatever that is. Okay, so now I think we can go back to the surface integral and start putting things into it. So evaluate surface integral. Well, it's going to look like the surface integral f ds, d capital S over the surface, is, well, I have to take f and evaluate it at the parameterization. Now the parameters are y and z. And then I multiply that by the magnitude of ry cross rz, dy dz. And then y went 0 to 1 and z also went 0 to 1. If you remember back from the parameterization here, when we first set it up, those were our bounds for y and z. Okay, so how does this work? It's going to be f at, well, what's the parameterization? Let's try to remember or go back and look at it. It's the parameterization is y plus 2z squared yz. Times, and then the magnitude of ry cross rz is the square root of 2 plus 16z squared dy dz. Are there any questions about where all these pieces came from? All right, now I have to plug into f. So this says evaluate f at this place. And what does f do? Well, our original function, f of x, y, z, the output is just the z value. So if I go back here, f of the x component, the y component, and z component is just the z component, which happens to be z for this parameterization. So this is going to be 0, 1, 0, 1, z times the square root of 2 plus 16z squared. And those of you in the know just breathed a huge sigh of relief because we've narrowly escaped trig sub, and because we have the du that our heart desires. So this is really, maybe we can see it better if I write this as to the 1/2 power.
Can you explain what happened there again?
To get from this step to this step?
Yes.
Okay. So yeah, so remember that our function f of x, y, z was a z. That was what given to us. So what that means is f of 1, 2, 5 is 5, and f of y plus 2z squared yz is z. It's just whatever this component was. So whenever I looked at this here, here's the x coordinate, here's the y coordinate, here's the z coordinate, the function said put the z coordinate as the output for f. So that's why that's what we put there. And then this part came from what we calculated above here.
Thank you.
Okay, so let's see. So if I took the derivative of the inside, I would have a 32z squared. So I really wish there was a 32 here, so I can fix that by multiplying and dividing by 32. And then I have a u and its derivative. If you want to do the u sub, your u would be 2 plus 16z squared, and you'd have to convert the bounds. But we're starting, I hope, to be able to see at least how substitution works. So I'm just going to go straight to writing. Oh, I don't need to do that right now because we're doing dy. This is still fine, but we're doing dy. So this is 0 to 1. Now I've got 32z 2 plus 16z squared, the 1/2, times y when I antidifferentiate with respect to y. So that's just going to be 32z 2 plus 16z squared, 1/2, times 1 minus 0. And now we can integrate with respect to z. So this u sub information should be down here instead. Darn it. Let me try that again. Okay, so then if I'm going to do the integral, it's going to be 2 plus 16z squared, the 3/2 divided by 3/2, 0 to 1. You can take more steps if you want doing the integral. I just don't want to spend a lot of time in class on this part because I know you can do this part. So these will cancel. Oh, whoops, that's not what I wanted to happen. These will cancel and I'll have a 16 down there. So I've got a 16/3 times 2 plus 16, the 3/2, minus 16, 16/3. Oh, what am I doing? Oh, gosh, it's not that at all. It's, so this would be a 16, so it's 1 over 48, I mean. Plugging in 0, I'm going to get a 2 to the 3/2. So I think I've got 1 over 48 times 18 to the 3/2 minus 2 to the 3/2. Are there any questions about that? Okay, so this, it's a little bit more than the surface area problems in that you're going to have to also evaluate a function at your parameterization, but everything else sort of follows along the same way that we've done earlier. This, these are fine, and sometimes you do have a real valued function that you want to integrate over a surface, but that's not the main event. The most common and the most exciting form of surface integral is the second type, which is surface integral of vector fields. So I'm about to go on to that, but let me just make sure I give everyone a chance to ask a question if they have it before I move on. Anybody? All right, let's talk about vector fields. Where did you go? This is the coolest. Okay, so remember that the line integral, well, what does a line integral of a vector field tell us? What was the meaning of that?
How well the curve is in agreement with the vector field.
How well the curve the oriented curve is in agreement with the vectors from the vector field. The vectors from the vector field. A surface integral of a vector field, instead of knowing how well do the vectors line up with the curve, it's going to say how well do they line up with the normal vectors to the surface. We get the normal vectors from the surface already. This RU cross RV from a while ago, this RU cross RV, these are normal vectors to the surface. So a surface integral of a vector field tells how well the vectors from the vector field line up with the normal vector to the surface. So this measures surface integral of a vector field. Tells us how well the normal vectors to a surface, and I'm just going to say to an oriented surface because I don't want to lie, are in agreement with the vectors from the vector field. Come on. So this is going to be hard to draw because it's a 2D thing, but imagine you've got some surface. How am I going to draw a surface that's not well, okay, so I'll draw a surface area. How about like I've got this surface which is a paraboloid, and then the normal vectors are doing, you know, what normal vectors like to do, which are sort of poking out perpendicular to the surface. And then, so these are the normal vectors. And then maybe, who knows what the vector field's doing? The vector field is maybe it's all going this way. Then what we're doing is we're trying to compare the vectors that are normal to the surface with the vectors from the vector field. And how do we do this measurement of agreement? What's the math that does measurement of agreement?
Is that the dot product?
Yeah, it's from the dot product, so we're going to use the dot product. As our measurement of agreement. So let's see, what would it mean if I want to know, I've got some surface here, and I've got some vector field doing something, and the parts of the vector field that are normal to the surface, I can think of those as parts of the vector field kind of passing through the surface, right? So whatever the surface is doing, if the vector field, if part of it is normal, that means it's sort of passing through from one side to the other. So some of you are engineers, and you might have even heard a word already that describes a vector field, to what extent a vector field passes through a surface. What word is that?
Is it flux?
Flux, exactly. What we're calculating is flux. So this is flux. That's the name for it. Okay, and so we're going to use the dot product, absolutely, because that's what tells us agreement. And we're also going to use this ds with a vector on it that we figured out last time. Because what does that give us? It gives us a normal vector to the surface. And as a bonus, it sort of gives you the size patch of surface that it represents. So it's got all the stuff that we need. So, so let me just define flux a little bit better. So imagine a vector field in 3 space. And a surface S. then the flux measures the rate of flow of F across S. In other words, sort of the volume. You could think of it as like the volume that passes through for unit time. Okay, but here's the catch. You need there to be a catch. So if I have a surface, let's say this piece of paper is my surface, and I have a vector field that's going like this. Well, is that in agreement with the normal vector? It depends, because I might choose the normal vector that is in this direction, or I might choose normal vectors that's in this direction. And if I choose the one that's in this direction, I would say that the vectors from the vector field are giving sort of positive flux. They're going outward. There's agreement between the vectors of the vector field and the normal vector to the surface. But if I happen to choose this normal vector, gosh, I don't have enough mass. If I happen to choose this, maybe you can see it, this normal vector, and the vectors from the vector field are going this way, I'm going to get negative flux. And we can't just let that be ambiguous. We can't just say, oh, it's either positive or negative, who cares? So what we really need to do is also choose an orientation. This was what we did for line integrals, remember, and that's why I sort of added this word oriented curve. We remembered that for line integrals, you know, the curve needed an orientation, it needed a direction we were going along it, so we could say whether the vectors from the vector were going in that same direction or whether they were in opposition with the chosen direction. But the chosen direction is kind of arbitrary. It's not like there's a best direction, it's just there's a direction given for the problem. Same thing's true for surfaces. Surfaces are going to need to be oriented in order to answer this question about flux. And there's two choices of orientation. And it's not like one of them is better than the other. It's just one of them is what's asked for in the problem and what's not. Let's talk about orientation. So orientation of a surface. So there's two directions that a vector field can pass through the surface. Yeah. So if I told you that the flux across the surface was positive, you wouldn't know which way the vector field was going. If I said the flux across this surface with this orientation is positive, you know that there was more going this direction than there was going this direction. So you need to know which direction are we talking about. That's what an orientation is. So an orientation of a surface is a choice of normal direction. I'm going to say it's a choice of unit normal because I only care about the direction. I don't care about the length that you're using to tell me the orientation. The orientation, there's only two orientations. There's that way and the other way. There's not like this way and twice as long this way and half as long this way. No, there's this way or the other way. So I'm just going to say unit normal. So we just disregard, we don't think about the magnitude whenever we're talking about the orientation. It's just a direction. And this choice is usually arbitrary. Okay, well, so let's think about it. If I have let's say I have a sphere, there's two choices. So maybe I should have made that clear. There are two choices. So for the sphere, for example, I could have this normal, or I could choose this normal. I would call this one the inward, and I would call this one the outward. Maybe I should move that over actually. So examples. So there's two different choices of normal, and I would make a choice and say, let's use the outward normal or let's use the inward normal. But sometimes outward and inward don't make any sense. So for example, if my surface was a plane, and I said, use the outward normal, you'd be like, what are you nuts? It doesn't make sense at all. So I'd still have two normal directions. One of them would be kind of like this, and the other one would be like this. So in this case, I might call these the downward and the upward ones. There's sort of no universal name for them. It depends on what the shape is. So look at the shape, decide about one, which will describe which way you're going. Okay. And let me just notice, but I can't help it because I'm a topologist, and this is super cool. Some surfaces are non-orientable. That means you can't put an orientation on it, non-orientable. And so a classic example, have any of you heard of the Mobius band? You know what that is? It's like if you take
that represents one dimension.
the Mobius band, well, the Mobius band is a two-dimensional thing. Let me see if I can make one real quick. So for a Mobius band, you take like a strip of paper, and normally, you would just sort of fold it around and have it attach. This would be an annulus or a cylinder. But let's suppose you got weird, and instead of attaching it this normal way, you put a half twist in this before you attached it. That's called a Mobius band. And if you do that, this is a non-orientable surface. Turns out whatever you think is the outward normal is the same as the inward normal. There's only one normal direction. So here's a drawing of the Mobius band.
Would the same logic apply to like Klein bottles as well? If we were
Yeah,
given
Klein bottle is also non-orientable. Yeah, exactly. So in this Mobius band, if I tried to choose, let's say I thought it was the outward normal, then that would be outward like that. That would be outward like that. That would be outward like this. But suddenly when it flips around, it's the inward normal. So there's no consistent choice of normal. The outward is the inward. So yes, if you've ever heard of the word non-orientable surface, this is what's meant by that. This is the type of orientation that we're talking about. Okay, so so just as before, remember what we did for line integrals. Remember for line integrals, the question asked for a certain orientation. We produced a parameterization, and that parameterization itself gave an orientation. And then what did we do with those two pieces of information?
Compare them.
Compare them. And if they agreed, orientation preserving. If they disagreed, orientation reversing. And then we went on with our lives, right? That's exactly what we're going to do now. As before, the question is going to ask for a particular orientation. Our parameterization will give its own orientation. And then we're going to ask, then we need to check, do these agree? And if they do, we say it's orientation preserving, or disagree, we say it's orientation reversing, just like before. Except, not like before, checking the orientation is quite a bit more work than checking the orientation for line integrals. So, in case you forgot these words. Okay, so we will need to check the orientation. And we'll do that when we get to an example. Okay, so just if in terms of calculating flux, well, I can tell you what the formula is for the flux, but let's do that in a minute. So calculating flux. So what are you going to need? You're going to need a vector field F with 3 inputs and 3 outputs. You're going to need a surface S in R3 with an orientation. And these are going to be your steps, okay? First of all, just like every single problem you've done for the past month, the very first thing you do, parameterize the surface. We need some way to get our hands on the points on the surface. And the parameterization is what does that for us. So parameterize S. So let's say it's some R of U and V. And there's some U bounds and some V bounds. Parameterize. And then we're going to calculate R sub U cross R sub B, just as we've done before. And this gives us a normal vector to the surface. And then part 3, we want to check whether this choice of normal that comes from our parameterization agrees with the orientation given to us in the problem. So check whether orientation preserving, or orientation reversing. Then once we've done all that, here's what our surface integral is. The integral over S of F dot D big S with the vector is the double integral, bounds for U, bounds for V. I don't care about the vector field everywhere. I only care about the vector field at the surface. And to get points at the surface, I plug in the parameterization. I want to know how well it agrees with the normal vector, so I take a dot product to measure agreement of 2 vectors. And then normal vector to the surface, that's represented by this ds. We had this in the notes from last time, but let's write it again. The ds is just going to be, I don't need parentheses there. It's going to be r sub u cross r sub b. That's our normal vector to the surface with sort of patch of surface area built into it. And the last little piece, which is the same thing we did for line integrals of vector fields, was we either added a plus or a minus depending on whether it was orientation preserving or orientation reversing. Okay. Let's suppose you're finding yourself overwhelmed with all this notation. I get it. Let me remind you of this thing that we have. Let me try to find it. About this one. Okay, so I'm gonna share this screen instead. So this is the this is in your class web page. So look, if I look on the web page, I went down to line and surface integral notation. And this is what I have. So here's all everything we had for curves. Here's everything for surfaces. It's got the exact same thing. Surface area, we just integrated the absolute value of something. We integrated the little patch of surface area. Here we added up the little patch of length for arc length. For the real valued line integral, we did the value of the function times this magnitude. For the real valued function here, we did the value of the function times this magnitude. It was more complicated down here, but it's the same idea. For the vector field, we did the vectors from the vector field dotted with the appropriate vectors from the parameterization. Vectors from the vector field dotted with appropriate vectors from the parameterization. Okay, so it may help you for a while to print this out or have it available when you're doing all these integrals. So it's there for you, just in case it will help. Okay, so I'd like to do a problem, but let me just take a moment to see if anybody wants to ask a question before I do. Okay, let's try a problem. Maybe that will. Let's evaluate the surface integral f dot ds, where S is the surface, with outward normal cut from z equals 4 minus y squared by the planes x equals 0, x equals 1, z equals 0. And the vector field is, where am I? Oh, this was when I was going to assign you for classwork. So I'm going to write that down for a second, and I'm going to do a harder one in class. So let me just, since I started writing it, let me just finish. It's going to be z squared x minus 3z. So this will be classwork. But sorry, the exercise, I want to do a couple of examples first. So let's do some examples. This one's probably a little bit easier, but as a warm up. And then I'll do a harder one. So this is just the identity function, the identity vector field. And what does this one look like, by the way? Do you remember what this vector field looks like?
Expanding outward.
Yeah, that's right. This one's expanding outward. So over the sphere of radius 1, using the inward pointing normal. So I'm sorry I didn't catch who just said that, but somebody just reminded us that this vector field is an expanding outward from the origin. And I'm using the sphere with the inward pointing normal. What do you think the value of the flux is going to be? Positive, negative, 0? What do you think?
Negative.
It's going to be negative. That's right, because the vector field's going out, but we're asking to what degree is it coming in? It's coming in sort of a negative amount. So we expect a negative value. Let's try it. Okay, so what's the very first step? Always parameterize. Okay. We know how to parameterize the sphere. It's a sphere of radius 1. So we don't need to use the radius, we just use theta and phi. And that's going to be 1 sine phi cosine theta, sine phi sine theta, and cosine phi. For theta between 0 and 2 pi, and phi between 0 and 2 pi, 0 and pi. Okay, if I'm going to do this integral, I need r sub theta cross r sub phi. So let's get in there. Okay, so r sub theta is sine phi, sine theta, negative sine theta, sine phi cosine theta, and 0. We've done a problem like this before, so I can go a little bit more quickly. And then the derivative of sine phi is cosine phi. Cosine theta just comes along as a constant. And then negative sine phi. And then the cross product is kind of ugly and then satisfying. Don't memorize this, because memorizing something isn't showing me that you know how to do it. And I want to know that you know how to do it, so do not memorize. Or if you memorize it, you still have to show me the steps. Memorize.
The second component of r sub d, is that supposed to be sine theta?
Yes, it is. Thank you for fixing that. Is that Tom? Thank you, Tom. Wait. Of r sub phi? Let's see.
Yeah.
This one, I think this one's supposed to be, oh no, I think this is right. This was cosine theta. Let's see, r sub phi.
R sub d, right? For the second the partial we did.
That's right. Let me make it obvious. So that should be sine theta. That's the one. Yeah, thank you. You're right. That would have gotten really ugly if I didn't have this right. Okay, so let's see, ijk. I'm going to put in first negative sine phi sine theta. And then I'm going to put in sine phi cosine theta and 0. And then I've got cosine phi cosine theta. And then cosine phi sine theta. And then negative sine phi. And I have to rewrite the first two columns. So negative sine phi sine theta, sine phi cosine theta, cosine phi cosine theta, cosine phi sine theta. Okay, and then doing this cross product, I'm going to get the forward thing, I'm going to get minus sine squared phi cosine theta minus 0. And then for j, I'm going to get 0 minus a minus a minus, so minus sine squared phi sine theta. And for the k component, I'm going to get minus sine phi cosine phi sine squared theta minus sine phi cosine squared theta. And I can simplify that a little bit. If you remember, we did this last time. If I factored out a sine phi times cosine phi, what's left over is sine squared times cosine squared. So simplifying this a little bit, I can get negative sine squared phi cosine theta, negative sine squared phi sine theta, and then negative sine phi cosine phi. Now the next step said to check the orientation. Check whether orientation preserving or orientation reversing. So the question is that outward or is that inward? You can't tell just by glancing at that. You might think, hey, negative values, negative means inward. No, it doesn't. I mean, if I'm at the bottom, it's pointing up inward. And if I'm at the top, it's pointing down inward. I mean, that's just not related. So you can't tell from just eyeballing it. We have to get into it. So let's just think what a good thing to do in this case, and there's different things that work for different surfaces, and we'll try a whole bunch of things. A good thing to do here is figure out a point on the sphere where you know what the parameters are to get there, and you can write down the inward normal vector yourself. So what's a good point on the sphere where we can do that? Does anybody know the parameters at any point on that sphere? Well, a lot of times people will pick the North Pole. The problem with the North Pole is the North Pole has phi equals 0. That's true, but theta equals anything would still get me at that same place. So there's some ambiguity there. I don't pick that one because of that weirdness. I'm going to pick this point right here, which is the point 1, 0, 0. Because I know the parameters there. So at the point 1, 0, 0, parameters are, well, what's theta?
Is it pi?
Theta, oh, actually, if I was over here, theta would be pi, but since I'm around in the front, theta is going to be 0. So theta equals pi would be sort of back around on this side. And then what about phi? Phi rotates down from the top down to pi over 2. Okay, so the desired orientation is inward. And inward from this point would go negative in the x direction, 0 in the y, 0 in the z. So the inward would be something like negative 1, 0, 0. What does our parameterization give? In order to find out, we have to look at our parameterization. So this is our r theta cross r phi. That's our normal vector. And the question is, which direction does that normal vector point when theta is 0 and phi is pi over 2? So we plug that in. It's going to be negative sine squared of pi over 2 cosine of 0. Negative sine squared pi over 2 sine of 0. Oops. And then negative sine pi over 2 cosine pi over 2. And then, well, hey, this is 0. This is 0. And this is 0. And this one's 1. So I'm going to get negative 1, 0, 0. And I'm going to say, hey, this is it orientation preserving or reversing?
Preserving?
Preserving. Okay. I don't have time to do this surface integral, unfortunately, and this is a horrible one to start fresh on. But that's what we're going to do. So next time, I'm going to start with, I'm going to just write down the parameterization. I'm going to write down, it's a different color. I'm going to write down this cross product that we already got to. Just going to remind you, and then we'll keep going from here. You'll already have it in your notes, but I'm going to have to rewrite it sort of shorthand. So to be continued. But the good news is tomorrow you can do 13.6, and you can also do 13.7 real value. But we haven't done nearly enough to be able to do 13.7 vector field, so we'll hold off on that until whenever we can. I think we might finish 13.7 vector field tomorrow, and then we'll be able to do Stokes' theorem and maybe also the divergence theorem in the next class, and then we might have a little bit of extra time to practice. Let me also say, even though you can go now if you want to go, but I'm just going to give you sort of a possibility. If you want, I could set up times after class ended, but before the exam, where I would just sit here and you guys would work on problems, and I can be here to answer questions while you're going through it, because I like to do that in general, but since we've missed so many days, we don't really have time to do that. So if anybody wants that, send me an email about it and I'll try to set something up. If nobody wants it, I won't waste my time. Okay, good to see everybody. I know this is hard. We're gonna get right back into it tomorrow, and it'll start to reinforce things, and it'll get easier and easier. And I'll see you tomorrow.
So just to clarify, we have 2 homework assignments due tomorrow, right?
Yes, that's right.
All right, thank you.
Sure.
Thank you.
You're welcome. Bye. I'll see you tomorrow.
Professor.